Good morning. I'm Dave Conway, President of CCDEH. I'd like to thank everyone for attending today. I'd also like to thank Hedgerow for sponsoring our event. And remind everyone that the virtual training series, you can go into ccdeh.org and look at the training series. Any series that you've missed, you can go back and look at. And don't forget to do your evaluations at the end to be able to get your REHS credit. Make sure when you are asking questions on the session that you use the Q&A button at the bottom, not the chat. And give Tim a couple of seconds here. I'd like to now introduce Vicki Jones, Merced County Environmental Health Director and Water and Land Policy Committee Chair, to introduce today's topic.
Thank you, everyone. I really appreciate everybody joining us today. We are here to learn through the water and land section for today's topic. The title of today's session is Augmented Reality, an overview of alternate water supply options. And this is an interesting topic, especially during this time as we are experiencing drought in California. Our presenter today is Jim Blanke. He is a senior principal and hydrogeologist with Woodard and Curran. He has over 20 years of experience helping public agencies manage groundwater in California, including development of groundwater management plans under the Sustainable Groundwater Management Act, or SGMA, development and implementation of groundwater ordinances, analysis and management of groundwater substitution transfer programs, development of groundwater banks, development of recharge projects, management of salts and nutrients, development of monitoring programs, and analysis of groundwater management options using groundwater models. And so with that, I would like to introduce Jim Blanke.
Okay, thank you, Vicki, and thanks everyone for the opportunity to speak to you today. As Vicki mentioned, here to give a presentation, Augmented Reality, an overview of alternate water supply options, and really appreciate the opportunity to speak to you today because there are a lot of people involved in the water supply world and making sure that everyone in the state has access to safe, reliable water supplies, and the folks on this call are an important component of it. And there are a lot of folks involved and a lot of complexities involved in the water supply system and kind of what the options are to improve water supplies for all of our users of water across the state. So with that in mind, the goal today, given we only have an hour and a half, is to really go through a high-level overview of the drought and potential long-term water supply options. So I do have long-term in there, so we're looking at things that are not things that would necessarily help with the drought today or the drought next summer, but things that would help with the drought and future droughts and long-term water supplies as we try to make sure that we balance our supplies with our demands. We'll also touch briefly on the Sustainable Groundwater Management Act and how groundwater sustainability agencies fit into these potential supply options. So we'll talk about how county entities and folks on this call can interact with that Sustainable Groundwater Management Act or SGMA process to stay involved and to help guide that process towards a successful conclusion. And finally, talking about how to engage in that overall water supply planning and how folks on this call might play a role in that. So, agenda in 4 parts: drought background, response options and feasibility. That's where we get into the water supply options. The GSA responsibilities, what they're doing, and engagement, how folks on this call can engage in that water supply conversation. So we'll start with the drought background and dive right into the drought that we're all, of course, aware of. But it really is, this year's drought has been really one of the driest that we've had. It's produced declines in surface water storage, declines in groundwater levels that are really pretty exceptional, even compared to the last drought that we had in the 2014-2015 time period. So this map on the screen here is showing the U.S. Drought Monitor's map of California. You can see on the right that they have different colors of intensity for the drought, from white to this kind of a deep red color here, with the deep red being exceptional drought. You can see across California, a substantial portion of the state is in that kind of deep red exceptional drought color. That swath of that deep red covers the entire Central Valley, covers most of the Bay Area, goes down a little bit into Southern California. And the bulk of the rest of the state is still in this extreme drought territory. So where most of our agricultural lands are, where most of our large cities are, where our big reservoirs are, these are all in areas that are experiencing extreme or exceptional drought. And so that exceptional drought is defined by the U.S. Department of Agriculture as exceptional and widespread crop and pasture losses and shortages of water in reservoirs, streams, and wells, creating water emergencies. So you can see the bulk of the state within that categorization there. Some exceptions there are in the far southern portions of the state where it's still a moderate drought. And those are areas that aren't particularly, they don't get a lot of rain in general. And there are no large reservoirs and no large components of the water supply system that are dependent on rain in that part of the state. So really the parts of the state that are critical on the water use side of things and on the water supply side of things are really in this deep drought right now. And the impacts are broad. I know we all think about the impacts of drought, but a lot of it's even broader than you might think. So we know that it impacts farmers. We know that it impacts a lot of individual well owners where their wells go dry, but it goes beyond that. So there's fallowing of fields where farmers don't have enough water to grow their crops. So they have to not plant that field or let those crops die. If they have a little bit of water, but not quite enough water, there can be lower yields from those fields. We've seen a lot of fires this year. The drought can increase opportunities for fires. We had a very dry spring this year, so things started drying out earlier than usual. The rain that we did have came pretty early in the winter time period, so there was a little bit of water and moisture to kind of grow those fuels. But then dry weather to help it dry out earlier and not only fuel fires for this year, but in future years, we're likely to see additional fuel from dying trees and other impacted plants from the drought this year. Impacts to recreation, we're seeing the reservoirs go down earlier, seeing streams running lower, impacting opportunities to go out on those lakes and boat or go out in the rivers and raft or fish or things like that. Fish rescues, needing to rescue fish where stream flows get too low. Insect issues, again, kind of attacking these trees and plants that are stressed from the drought. Flora and fauna impacts where the plants and animals aren't getting enough water. Increased ag unemployment when these growers have to fallow their fields or their yields go down. There's less work for people to do, particularly in a lot of our disadvantaged areas that are dependent on ag employment. So a lot of impacts from that as well. Air quality issues driven by fires, driven by fallowed fields and dust and things of that nature. West Nile virus, which you would think would be correlated more with wet periods, but we see a lot of West Nile virus come out during drought periods where water can become more stagnant with the decreased flows coming into different man-made systems. And water shortages, curtailments, higher prices, dry wells, water quality issues, more of the typical things that at least I think about when I think about water. Where there's just not as much water available to farmers, not as much water available to cities, not as much water available to domestic well owners, and associated water quality issues that can come from those lower flows. So really a broad suite of impacts coming from the drought. Okay, and at the base of this, and most of our water supply is coming from surface water and from groundwater. It's impacting both. So this screen has a couple of things on it. We'll start on the right-hand side here. And on the right-hand side, we have a map from the California Department of Water Resources that shows the major reservoirs in the state. So there's a dot for each of the major reservoirs. They're labeled, and each one has this little bar chart here. And so if we look at Lake Shasta here first, we can see the total storage here is up at the top, and that's a little hard for me to read, but it looks like 4,552 thousand acre feet, so about 4.5 million acre feet there is the total storage. Typically, this time of year, we're at this red line, so that's the historical average. So late summer, the surface water levels in all these lakes are already drawn down because, of course, we don't get a lot of rain here in California in the summertime, and so those lakes fill up in the spring and they're drawn down during the summertime as we use that water for various urban agricultural and environmental uses. But typically that water gets drawn down to that red line. You can see right now we're down here at this blue bar. So we are substantially below the historical average for this time of year. And that's true for almost all of these reservoirs across the state. And so because of those low water levels, excuse me, in the reservoir system, that's the cause for a lot of the curtailments that you hear about. So curtailments are reductions in the amount of surface water that are made available to folks that have access to surface water across the state. In addition, groundwater is an important component of our water supply. And so groundwater is not as easy to measure, it's not as easy to monitor as our surface water system. The surface water system, you can go out and you can pretty easily measure the elevation of that reservoir and watch that water fall, and it doesn't really matter which part of the reservoir you measure it in, that level is going to be the same. But the groundwater system is, of course, a lot more complicated. It varies a lot, both vertically and horizontally, and it's you have to drill a well in order to get that measurement. So what we're looking at here is what we call a hydrograph. It's just a chart of groundwater levels taken over time. In this case, we have groundwater levels from about 2000 through present, and we have elevation here on the vertical axis, 80 feet, 90 feet, 100 feet above sea level. This red line is ground surface. And you can kind of see how they've responded over time, and that they kind of go up and down a little bit. So there's some kind of natural variability in there, maybe some impacts of wells pumping and things like that. You can see they went down a little bit during the drought period here, 2014, 2015. But they came back up as it got a little wetter, that wet 2017 that we had, and then into some more normal years, a little bit drier in 2020. But then in 2021, really steep drop-offs. And we've seen these steep drop-offs in a lot of the state, and it's driven by a couple of things. One is more groundwater pumping. And so a lot of times what happens when we see reduced surface water availability from all these reservoirs and rivers and streams that we were just talking about. If that water is not available, often there's an opportunity to pump groundwater to replace that water. And so as you increase pumping to substitute for that surface water supply, the groundwater levels are going to drop because of that. Another one is less recharge. So there was, of course, less recharge over the past winter. Because we didn't get as much rain, and so there wasn't as much recharge from the rain, and there also wasn't as much recharge coming off the rivers and streams because the rivers and streams weren't flowing as hard as they usually are. And so that combines to create lower groundwater levels. And I guess the other component is, I did mention earlier, the dry spring that we had. So a lot of times, excuse me, in the springtime period, precipitation can satisfy some of the water demands that the crops have, but if it's dry, there can be additional needs for early irrigation. That likely occurred in a lot of the state this year because of that dry spring time period. So those groundwater levels drop, and what that means is when those groundwater levels drop, that can endanger some of the more shallow wells in the area. It can also impact ecosystems where groundwater levels may be feeding creeks and streams and rivers, or groundwater levels may be feeding plants that are reliant on that groundwater. And of course, a lot of domestic wells are shallow. So we typically see that the agricultural wells are larger and deeper than the domestic wells. And so a lot of those domestic wells are the first signs of impacts of these lowered groundwater levels. going into a little bit more detail on the surface water. So we looked at those charts for surface water levels across the state that the Department of Water Resources develops. But one thing I wanted to talk about is carryover storage, and that is important for the drought conditions that we see now, and it's important for the drought conditions that we might see next year if we don't get much in the way of rainfall this winter. So if we look at this chart, this is specifically for Lake Shasta. That was the first lake we looked at earlier. The numbers here are a little bit bigger and easier for me to read this morning. So about 4.5 million acre feet. It's a very large reservoir. And total capacity is up here at this blue line. And what this chart shows is it shows monthly information. So October through September here. And this blue kind of wave is the historical average, right? So in October, typically it's at its lowest. Once the rains pick up in December, January, it starts going up. It peaks with that precipitation and the melting snow around April and May, and then goes back down again in the summertime as that water is released to meet all the downstream needs and because of the reduction in inflows to the reservoir. So that's the normal year there. This red line is the recent history. So that's 2020, October 2020 through just the end of September, just a week ago here. So you can see that we started just a little bit lower than normal. But when we went into the winter time, it didn't go up very much. And that's because of the lack of snowfall, lack of precipitation. And then, of course, we still had needs for that water, so it went back down again. So the drought caused the reservoir not to fill up, and that put us in the position where we are now, where the reservoir is quite low. Now, when we start this year, I don't have a similar map, but you can take this endpoint here. Our starting point for this year is now down here around, looks like about 1 million or 1.25 million acre feet. So we're substantially below where we were last year, about 1 million acre feet lower than where we were last year. So if we have another similar year, we don't get much recharge, then we're going to start being in worse condition as time goes on. So this is true in Shasta. This is true in the reservoirs across the state. This is Folsom Lake, located outside of Sacramento here. And then this one is Lake Oroville, which is another very large reservoir, of course, near the Oroville area there. So you can see all of these show that this water year, starting in October, we're starting from a much lower point than we did last year. And that lack of carryover storage means there's just less money in the bank this year to meet the demands of next year. So that's the importance of getting some good rainfall this year is even higher. Okay. So next section, into response options and feasibility. So the first thing is that the easy water is gone, the cheap water is gone. So the picture here is actually from Merced County from a long time ago, and it was at a time when you could drill a pretty shallow well and water would just naturally flow out of that well. So flowing artesian well is caused by the high groundwater levels in that area and being capped by clay that actually pressurized that water. So there was a time when water was pretty easy to come by, and that time is gone. So finding new water supplies requires some creativity and some local knowledge. So there's no one size fits all solution to water supplies across the state. So it really requires understanding the local conditions and opportunities, and that's not just for water and not just for water supply. It also is related to achieving multiple benefits because a lot of these water supply options can be quite expensive. They can become more feasible if you can achieve other benefits, whether that's water quality benefits, recreation benefits, anything like that can also make these things pencil out better. So we'll go through several options here in our toolbox here. This is a big long list of options, and we'll go through each of these briefly, provide a couple of examples, and talk about some of the basics about what they are, so that when you're involved in conversations with folks on some of these water supply options, you'll have a better background and be able to process a little better how it might work in your local area. So we'll start with recycled water here at the top. And go through recycled water first because it tends to be a pretty good option for a lot of areas within California. It does require, of course, an urban area with adequate effluent. So recycled water is taking water off of that urban wastewater treatment plant, treating it to the appropriate level, and then delivering it for reuse. So the first thing you want to do is kind of think about, do you even have an urban area with a wastewater treatment plant? So you have to have that. That's a requirement. And if you do, the next question is, well, what is that use of the effluent right now? So in some areas, that effluent may be discharged to the ocean, in which case it's not really being put to any use at all. But in other cases, it may already be applied to agricultural crops. So there may already be a use for that. Or it may be discharged to a river or stream, in which case you have to consider what the potential impacts might be of taking that water out of the river or stream, which can be negative from a flow standpoint and can be positive from a quality standpoint. So there's a lot to unpack there as far as what that current use is. Couple of things to think about is that the projects typically require substantial infrastructure to deliver water. So to put in a recycled water project, typically these projects are for irrigation purposes, for agricultural irrigation. So you have to be able to get that water from the wastewater treatment plant to the growers. So there's typically a lot of piping involved to get that, and a lot of coordination with the growers and providing on-farm infrastructure to get that water into the grower system. So there can be a lot of infrastructure required to get that put together. And oftentimes, because of the way our sewage system works by gravity feed, those wastewater treatment plants are in geographically lower portions of the regions that they serve. So oftentimes it can require some kind of pumping to get that water back up to the areas where they need to be used the most. The other thing to think about is there are different uses for recycled water, and those different uses require different treatment and permitting and just a variety of different ways to put it together. So I talked about irrigation, which is pretty straightforward, treating your water to the appropriate level and then delivering it for growers, and they can use that water instead of the surface water that they're using, or maybe instead of the groundwater that they are using, or maybe it's new irrigation that's occurring. Another option is indirect potable reuse, and so that's taking the recycled water and recharging it into the groundwater system, or discharging in surface water system, having some kind of a environmental buffer between where that water is recharged or discharged and where it is picked up again later by a well or other facility for later use. This is something that's also fairly common. Orange County Water District is probably the largest user of indirect potable reuse. They have large ponds that they constructed along the Santa Ana River down there, where they put a lot of recycled water in the ground, and that water is put in the aquifer and is later extracted by a lot of wells across the region to help provide for a sustainable water supply down there in Orange County. Direct potable reuse is taking that water and directly putting it into the potable water system. That's not something that's being done in California, to my knowledge. It is being done in the United States. It does require a substantial amount of public outreach to gain acceptance on that kind of practice. But things are definitely moving in that direction across the country. I believe in Texas and New Mexico, some projects along that lines down there. And these different things require different levels of treatment. Obviously, direct potable reuse, indirect potable reuse involves substantial treatment. On the irrigation side, there can be a lower level of treatment there, as the plants are able to use up a lot of the nutrients and other constituents within that water supply there. So be a little protective of the water quality. So as far as water quality, the projects, of course, have to consider water quality, because recycled water can have higher concentrations, specifically of salts and nutrients. Also, personal care products, things like that, are also concerns. So typically that water quality concern is addressed throughout the process to make sure there's not an impact to the underlying groundwater quality. Salt and nutrient management plans are often a way to achieve that, which involves analysis, kind of a holistic analysis of salt and nutrient loading to the groundwater basin, looking not only at the project that's being proposed, but also what else is going on in the groundwater area, to see how those concentrations of salts and nutrients might change over time, and if it would impact the beneficial uses of water. On the plus side, the costs are much lower for non-potable ag use compared to potable uses, and they're lower compared to a lot of other of these kind of next phase water supply options. And it is pretty drought proof. Effluent levels have gone down, so the effluent volumes have gone down with conservation over the past 5-6 years, but it's not as dramatic as what you see the reduction in water supplies in our surface water system or groundwater system. So pretty drought proof there. As an example, here in the Sacramento region, Sacramento Regional County Sanitation District is putting together their Harvest Water program, which is intended to deliver 50,000 acre-feet per year of recycled water to 16,000 acres. It's being used for agricultural irrigation. So a lot of the growers in the area are using groundwater. And so instead of using that groundwater, they would receive this recycled water supply, and that would in turn store that water in the groundwater system, which would cause groundwater levels to go up, and that would have benefits to stream flows and to habitat. So it's in an area of important riparian habitat, and also in an area of the Cosumnes River that's been impacted by low groundwater levels, resulting in a lot of the water from the river seeping into the groundwater system. So it's intended to address those conditions. Another component is a wintertime application, which is looking at applying the water in the wintertime to support sandhill crane habitat. And the project itself had its origins with an order where the sanitation district had to improve their treatment system under order by the state to remove constituents from the effluent. And that required treatment, opened up a lot of opportunities, and the district wanted to put that water to use now that it was being treated to a higher standard. So it's again kind of looking at these multi-benefit and kind of some of the unique nature of conditions in your region, where that requirement for a change in the treatment kind of allowed for this project to move forward, where it may not have if that treatment requirement hadn't come up. Ocean desalination is always a hot topic. I think the first one here is that you have to be next to the ocean to do ocean desal. I think that's I think one of the more obvious things. We have to be close to the ocean, and there are environmental considerations. There's substantial environmental considerations. First is the intake. There are potential issues with entraining sea life in the intake process to get the water out of the ocean and into the desal plant. There are ways to try and get around that with using things like some of the slant wells that they're looking into in the Monterey area. So you can put a well close to the ocean, maybe even slant it out so it's kind of angled down towards the ocean direction, and pump in some of the seawater from below the surface, so you avoid entraining some of that sea life. Also issues associated with the brine outfall. After you treat the water and you have your clean water, you also have a super salty brine you have to dispose of. So that brine has to be disposed in a way that doesn't damage the sea life. So that's another environmental challenge associated with desal. I guess the fourth bullet is also an environmental consideration. Is very energy intensive with the desal process, basically taking the seawater and through a reverse osmosis process, removing the salts. It takes a lot of energy, which is a big component of the cost of desal. So there's a lot of permitting regulatory hurdles you have to get past to do desal, but it is of course drought proof. The ocean's going to be there in the future. An example is one that's been in the news a lot. The recently opened Carlsbad facility produces 50 million gallons a day, about 56,000 acre feet per year. So similar in scale to that recycled water project we were just talking about in the Sacramento area. does use the reverse osmosis process, and it supplies about 8% of San Diego County's water supply. So it is a small but pretty substantial portion of the water supply, and important because it is a drought-proof component. It costs about $5 per month per homeowner, but the overall water costs are a little over $2,000 per acre foot, which is pretty expensive water, but it is a price tag that a lot of urban users are willing to pay. It's not a price tag that an agricultural customer would likely be willing to operate under. Next one is very similar, but it's groundwater desalination. So groundwater desalination is doing the same thing that ocean desalination is, but instead of using ocean water, it's using groundwater. So a lot of our groundwater is saline, so it's not as salty as the ocean, but it is too salty to use. And with continued use and reuse of water, the salts tend to build up in the groundwater subbasins. And so that can eventually result in groundwater that is too salty for use, whether that's too salty for agricultural use or too salty for urban use. So groundwater desalination has a couple of advantages. One is it avoids the ocean intake issues, so you're not worried about sucking up any sea life there. Another is that it requires less salt removal than seawater. So because that saline groundwater is not as salty as seawater, there's less salt you need to remove, which lowers the energy cost of the process. On the negative side, it does require brine disposal, and oftentimes with ocean desal, that brine is disposed of to the ocean in a way where it's not too concentrated, to avoid some of those sea life issues. But if you're inland, you have to be able to either pipe that water to the ocean or find some kind of alternate way to get rid of the brine that's left over once you remove the salt and produce that potable water. So that's probably the biggest challenge associated with groundwater desal. And just an example here, this is in Eastern Municipal Water District down in Riverside County. They have a very carefully managed groundwater system. They manage it pretty carefully with regards to salts and overall water quality, with regards to where do they recharge high quality water, where do they do their recycled water operations, and then where do they operate these desalters. So it's all kind of done with an eye towards a managed groundwater system. So they operate 2 desalters with a third one on the way, I believe. And in the process, they remove 50,000 tons of salt per year, which is important for this area because a lot of these groundwater basins down here do have elevated levels of salt that can impact their ability to be used for urban or agricultural uses. So it helps manage that total salt load in the subbasin. And it generates 13,000 acre feet per year of potable water. And they dispose of the brine through a pipeline. So they are fortunate to be along the Inland Empire brine line, which used to be called the Santa Ana River Interceptor. And so they're able to get capacity on that line and dispose of the brines through that way. So they're fortunate, despite being well inland, they do have a pathway to get rid of that brine. Next one is stormwater. So stormwater is capturing that local stormwater for recharge and use. So it's a little bit similar to surface water, but typically when people think about stormwater, it's kind of on that smaller scale, more local scale. These are often, but not always, smaller scale projects, and they often incorporate well with multi-benefit projects. So I think we'll go on this next slide with an example here in Malibu. So this is the Malibu Legacy Park Integrated Water Improvements Project. So it's at the terminus of Malibu Creek and it drains into Malibu Lagoon. This was put in quite a few years ago at this point, but it was put in less for water supply and more for water quality issues. So in this instance, there was a desire to address impairment for bacteria and nutrients that existed in the area. So what this does is it detains all the stormwater, and then it's treated and then released later. So it provides that water quality benefit that's necessary to help out some of the aquatic species in the area. And it also provides recreation benefit and some habitat. So you can see here on the picture, it's pretty conducive to walking trails and some of those other recreational opportunities. And so with stormwater, a lot of the ability to get additional water supplies can be smaller than some of the other supply options that are out there, but they can provide these other benefits pretty easily, and a lot depends on your local circumstances. So in some areas like San Francisco or Sacramento, some of the older cities that may have combined sewer systems, there may be benefits to trying to keep some of that stormwater out of the sanitary mixed sanitary storm sewer system to help with large storms and help with that overall process. Other areas may have flooding issues during storms, low-lying roads and things like that. So you may be able to take that water and move it into some place where it can seep into the ground rather than sitting on a road and causing problems for people. And a lot of water quality benefits can be gained by allowing that water to filter slowly through the ground, as opposed to trying to get it in the nearest pipe and whisking it off to the nearby creeks and streams. So a lot of benefits here. Water supply may be often a smaller component, but still very valuable projects that can be implemented. Surface water, I guess, is kind of an obvious one to look at, and obviously one maybe not to do, because a lot of our drought problems are because of a lack of surface water, right? So why would we look at surface water if we're already being shorted on surface water? That's certainly an issue. The use of surface water requires a water right, and in many cases, these streams are what are known as fully allocated. So the state has said that there's no more room for anybody else to take water off this river, so they won't allocate any more surface water rights to those streams. But in some areas, there may be water available during flood periods. And so this is, I think, where most of the focus is on surface water, is kind of this flood water that's available. So even in California, if you think back to 2017, we get these big years where there's just a lot of water, and the challenge is, how do we take those floods and put that water to use? And it's hard because those flows are big and they're infrequent, and a lot of the methods that we have to store that water have a hard time handling that. One of the things that we'll look at here on a later slide is potentially looking at agricultural fields and seeing if we can spread that water on agricultural fields at lower cost. That's a project known as FloodMar. Because if you want to have enough recharge basins for all this surface water and for major flood, it's just a huge area of recharge basins that's required in order to have enough area to get that all to seep into the water. And those recharge basins would be sitting empty most of the time. 80-90% of the time they'd be empty, and so it's just hard to make that pencil out. Another item here, areas of urban growth into surface water irrigated agricultural areas may benefit from the development of surface water treatment for potable use. We'll look at that one on the next slide, noting that it requires an intake and treatment for potable uses. So that is related to a lot of areas like Fresno, and so a lot of areas in the Central Valley, a lot of our cities in the Central Valley are growing into areas that are irrigated agricultural areas. So you have what we call ag to urban conversion, where you have a ag field that gets turned into a subdivision. And from a water use perspective, there's often not a large difference between the water use for an agricultural field and the water use for an urban subdivision. But often the difference is that particularly in the Central Valley and on the east side of the Central Valley, a lot of times that irrigated ag is irrigated by surface water, and a lot of times the cities are using groundwater for their water supply. So if you replace that surface water supply with a groundwater only urban supply, that can impact your your groundwater supplies, which are already really kind of being overdrafted in a lot of the San Joaquin Valley, at least. So one of the things that the city of Fresno did back in 2004 is they began treating surface water. And they have an agreement with Fresno Irrigation District. And Fresno Irrigation District is one of the major surface water purveyors for agricultural entities in the region. And so what that does is it allows them to use some of the water that Fresno Irrigation has, and it increases over time as the urbanization continues, allows the city to use that water for urban uses. And so that helps them to help maintain the sustainability of their groundwater system by not converting too many surface water irrigated lands into groundwater supplied urban areas, but instead introducing more and more surface water into that urban system and maintaining that overall supply mix for the greater Fresno region. Okay. Surface water reservoirs. So surface water reservoirs may be one of the first things that people think about for additional water supplies, because surface water reservoirs are what made California what we are today, right? Surface water reservoirs and aqueducts allowed for the cities and the farms and basically most of what we have here in the state today. They were, of course, the dominant water supply project of the 20th century. But those folks that sited those dams picked really good sites, and the remaining sites are typically lower quality, but they are there. They can provide benefits, but it's not the kind of benefit that you get from putting in that first dam. So that first dam is going to capture most of the available water, and you put in another dam. For instance, the dams that we looked at on those charts earlier in this presentation, you saw how the storage didn't increase very much over the winter time. So those dams don't have a lot of water behind them, not because there's not enough dams, but because there wasn't much water that came into them over the winter time. So you can get more dams and you can have more carryover storage. You can store some of that big flood water and some of the rainier year water that's available. But there is some degree of reduction in benefits that occurs as you add more and more reservoirs. And there are on-stream and off-stream reservoir options. We talk about, when you think about reservoir, you typically think about an on-stream reservoir. You have a major river, you put a dam on it, you back water up behind it. But we do have off-stream reservoirs as well. San Luis is one of such reservoirs. And so those reservoirs are, often they're still on small streams, but the bulk of the water is actually pumped into those reservoirs. The proposed sites reservoir in the Sacramento Valley is one such reservoir. So you pump water into the reservoir when there's a lot of water available, and then you pump it back out again when you need it. Some advantages of off-stream reservoirs is avoiding a lot of the natural river and stream ecosystems that are heavily impacted, if not destroyed, by surface water reservoirs when they're placed on those sensitive streams. So often there are environmental benefits to moving offstream, but even then there are, of course, substantial costs, permitting requirements, and environmental constraints for putting in surface water reservoirs. Most of the potential sites are known and have been studied. So there are often sites that are sitting there waiting for the appropriate water supply conditions, and that information is typically available for people to look at. So one example here is the Del Puerto Reservoir, which is located, which is planned in the foothills just to the west of Patterson. It is a locally owned and controlled project here with 82,000 acre feet of storage. So again, you can see this is a pretty substantial reservoir project for reservoirs going in California now. But if you compare that to the 4.5 million acre feet that we looked at for Shasta Reservoir earlier in the presentation, you can see it's actually quite a small facility here. It would have one primary dam, 3 saddle dams, and it would be, again, an off-stream reservoir filled by pumping water off of the Delta Mendota Canal when there is water available, and then be released back into the canal for farmers and wildlife refuges when needed. Okay, groundwater. Again, like I said, with surface water, why talk about groundwater when groundwater is, you said groundwater is falling and groundwater is an issue. But groundwater is what people fall back to, and that's where people go to when surface water supplies fail. And it's also depended upon by many of our vulnerable users, disadvantaged communities, and small water systems, and domestic well owners often rely on groundwater systems. So how do we get additional use out of groundwater? One is recharge, and trying to get more water into the groundwater system so that there's the ability to pump more water. So the more that you put in, the more you can get out, very similar to a reservoir, surface water reservoir. And those additional water supplies can be wet period surface water, like we were talking about with trying to get water in the ground with flood-mar, or with some of those flood period waters off of the rivers and streams. You can recharge recycled water or other available water supplies. And the other thing you might be able to do is you might be able to access poor quality groundwater. We talked about Eastern Municipal Water District and their groundwater desalination program. There are areas that have other contaminated water issues or are actively going through groundwater treatment. There may be opportunities to put that water to beneficial use where appropriate. Also want to touch on imported water. And this is, we talked about before with the reservoir. A lot of our imported water is coming from those reservoirs on that previous map/chart that we looked at from the Department of Water Resources. And so these are impacted water supplies as well due to the drought. But they are a substantial source of water, especially when you're looking at Southern California, San Joaquin Valley ag users, Bay Area, a lot of imported water making those systems work. There's not really the opportunity to get more imported water typically because they are they do experience issues during droughts for availability. But what is looked at are exchanges, banking, and transfers. So similar to what we were talking about with surface water and groundwater, it's how do you increase your reliability during drought, and how do you take the extra water that might be available during wet periods and store it or exchange it or transfer it so that there is an ability to use that water during dry periods. So there are opportunities for folks that have water and for those that have aquifer storage. And so what I mean by that is that if you have water, you may have some of this wet period of water. You may want to try and find somebody that has an aquifer system where you can put it in the ground. That can benefit both people. It can allow the person with the water to have access to that water later when it's drier. But for the person with storage, it can provide monetary benefits through storing the water, and it can also provide benefits to the aquifer system. Often those contracts are written so that some of that water stays behind in the groundwater system, and it can benefit the users in that area as well. Recharged and banked water. So we've touched on this on the previous slides. So a lot of water can be recharged or banked in the groundwater system. So you can take the imported water, recycled water, surface water, and storm water, any kind of water supply, and put it in the ground. It does require, of course, the water. You have to have the water. You have to have the rights to the water. And you have to have transmission facilities. So you have to be able to get it to the facility where you're going to bank it, and you have to have the facilities to get it into the ground. So this picture shows a recharge basin. This one's actually in Florida, but it shows a recharge basin. So you can see you could put water in that basin. It's got that nice sandy bottom to it, so that water would seep down into the groundwater system and be available for use later. And interestingly, in Florida, of course, Florida has a lot of water. Their recharge facilities are more of a disposal issue for recycled water than they are really more of a water supply issue. So it is, again, those kind of multiple benefits of some of these projects. Another way you can get water in the ground is through in lieu recharge. So that's what we mentioned for the Sacramento Regional County Sanitation District's Harvest Water Program, where you provide this alternate water supply, and then groundwater pumping is reduced because that additional water supply comes in. And by reducing that groundwater pumping, then the groundwater levels are able to rise and you store water in the groundwater basin that way. Another one that didn't make it on my bulleted list here is called aquifer storage and recovery. And that is a process where you actually pump the water into the groundwater. You form kind of a bubble of this recharged water, and when you need it, you pump that back up for later use. Aquifer storage and recovery is typically more used in areas where land costs might be too expensive for recharge basins, and there may not be agricultural users that are suitable for in-lieu recharge. Last item there is that banking requires extraction capabilities. So what's the difference between recharging water and banking water? It's really that extraction component. So if you recharge the water, you're really doing it for the benefit of the groundwater system, in some cases for the associated surface water and ecosystems at the surface if the groundwater levels get that high. With banking, you're also planning to extract that water later through a defined process. So two components, but very similar there. So this is one I mentioned earlier, a flood mar. So flood mar is a way to try to recharge floodwater on agricultural lands. It is one of the more hot topics in water supply options right now. And that's because we are looking at a time when the surface water is just not available. Sigma is really kind of putting a lot of restrictions on groundwater use. And so there's really a desire to try to figure out how can we recharge some of these low frequency, high volume flood events. So this has reduced costs associated with dedicated recharge basins because you're not buying up land, you're not stripping it clean and putting in that kind of sandy bottomed dedicated recharge facility that we looked at on that previous slide. Instead, you're continuing to grow crops on it. And in the wintertime, when maybe there's no annual crops planted, or when permanent crops like orchards or vineyards might be dormant, you can put the water on the fields and let it seep into the groundwater system. You have to do it carefully to avoid damaging the crops, try to avoid blowdown of the trees, make sure you don't waterlog the crops and damage the roots. But through careful management, it's been shown to be successful. One of the more common examples is down in the Helm area of Fresno County, where Don Cameron on his farm has had some success with flood mar activities on a variety of crops down there. But it does require careful management of crop health, as I mentioned, as well as water quality to make sure there's not any impacts to water quality occurring through the process of recharging this water on the ag lands. Urban conservation, conservation in general is more of a demand side thing than a supply side thing, but I wanted to hit on that. There's been good success in reducing per capita water use in California. We were about 231 gallons per day per capita in 1990, down to about 146 in 2015. Some areas of the state, especially the urban coastal areas, are substantially lower than that. There are opportunities to further reduce water use, but it does get harder and harder to reduce those numbers the lower it gets. And that demand does become hardened as conservation increases. And that means that it is, of course, harder to ask people to conserve water if they've already reduced a lot of their non-essential water uses. On the agricultural side, agricultural conservation typically includes improvements to irrigation efficiency and conveyance efficiency. So looking at things like switching from flood irrigation to subsurface drip or microspray or things like that can reduce the level of evaporation that occurs off the field, and it can also reduce seepage that occurs off the field. So that's the water that seeps down and past the roots into the deeper aquifer system. So from a water supply perspective, Less evaporation is good because that evaporative loss doesn't really help anybody. But that seepage, depending on where you are and how the groundwater system works, that seepage may be water that other folks are depending on to meet their groundwater needs. So that seepage component may not be a true saving. So it's worth looking at that to see if it makes sense. And that goes for conveyance efficiency as well. We do have a lot of unlined canals in the state, particularly in the Central Valley. But those unlined canals, while they do lose water out the bottom, in most cases that water loss out the bottom is being used by groundwater users. And so that's something that needs to be thought about if there's a desire to try to line those canals, because that would keep more water in the canal, but it would reduce that groundwater recharge that's occurring off that canal. Conservation could also be achieved through changes in cropping to reduce consumptive use. Typically, you don't see that happen very much, although with Sigma you might. The calculus by the growers is usually to maximize their profit. Of course, there is a cost to water, but that's not typically the primary focus. But conservation can be managed through crop change as well. Another more extreme version of conservation is land fallowing. So I did want to touch a little bit on land fallowing and in particular land repurposing, especially with this group. In many areas, land fallowing may be required to achieve sustainable water supplies. So if you look at some of the more impacted parts of the state, particularly in the southern San Joaquin Valley, there may be a need to reduce the acreage of irrigated lands. So part of the challenge is what happens to that land and how do we avoid impacts of having that land fallowed. So there is a growing call for land repurposing and making sure that land gets put to another good use that avoids impacts. And so those impacts can be air quality impacts and health impacts, thinking about dust, valley fever, impacts of those nature, as well as economic impacts. As we said before, reduced farming impacts our agricultural communities with fewer jobs. So how do you try to align these fallowed areas to achieve other benefits? And I have kind of a list of benefits here with habitat and trying to make sure that the lands are connected and not isolated patches of fallowed land. So they do provide better wildlife habitat, and also improving groundwater recharge, stream-based flow, water quality, flood protection, recreational opportunities. So these are all things that can be achieved by trying to fallow land in a carefully managed way that can provide these other benefits as well. Okay, so moving on to GSA responsibilities. The GSAs are ultimately responsible for regional groundwater sustainability. So it's called out in the water code. It's in the regulations, the groundwater sustainability plan regulations I have here on the screen. Bottom line, they're looking to try to avoid significant and unreasonable effects, which they define within their groundwater sustainability plans, and they're based on these 6 different sustainability indicators I have listed here: groundwater levels, groundwater storage, groundwater quality, depletions of interconnected surface waters, subsidence, and seawater intrusion. And oftentimes the focus is really on groundwater levels, and the other ones kind of follow along. So you'll see a lot of what they're trying to do is identify groundwater levels that could cause a problem in their basin and trying to set thresholds around those. So in that threshold development process, one of the considerations should have been, and in most cases was, domestic wells and trying to avoid domestic well dewatering. And I think that's an important component for this group to understand, because oftentimes I think this group probably has a better understanding of domestic wells than what the GSAs do. The data on the location of these domestic wells, the depth of the domestic wells, where the pump is set, and even which ones are even still in use is generally poor. Statewide data is generally coming from the Department of Water Resources. They have these well completion reports, which most of you are probably familiar with, but they provide limited information and poor geographic information. Oftentimes there's better data available from the county, or if there's a city well permitting agency, whoever's doing the well permitting, that can often be better. So if there's really a need to try to improve these kind of domestic well data sets, and to make sure there's proper communication and coordination so that the best data is shared, because this domestic wells are really an important component of determining how low groundwater levels can get before they really become something that causes significant unreasonable effects. The GSAs move forward with the best information they could find, but because of these data gaps, they may have developed thresholds that could be either overprotective or underprotective. So there's a real need to try to refine our data on domestic wells. Another thing for this group to consider is that what GSAs may not do. They may not be responsive to what I have in quotes here, smaller issues. So they are focused on significant and unreasonable effects. So small isolated areas that are having water supply issues may not be something they respond to. May not be able to rely on them to cover a lot of the issues that have typically been covered by the county. The other one is to mitigate for impacts. So they do describe some of the potential issues, but when groundwater levels get low, there may be impacts that are not significant and reasonable, and there may even be violations of thresholds that may result in state intervention. But it doesn't necessarily require mitigation for impacts, so mitigation for dry wells or other impacts to users. Although there are some groundwater sustainability plans that do include some kind of mitigation, but that's not universal across the board. They may not fully value multi-benefit projects, so they are focused on water supplies and to a lesser degree water quality, but they're not really focused on surface water quality, and they're not really focused on stormwater, on all these other needs and recreation and things like that. So they need to coordinate with others to try to make sure they see the benefits and have some of these more complicated projects be able to come to life. They may not have the capability to improve supplies. A lot of these GSAs are newly formed. They may not have the resources that they need to move forward. You'll find the capabilities of the GSAs vary widely across the state, with some of them very advanced and some of them really just struggling to meet what the state is telling them to do. They may also not have a focus on public health. So when they look at wells and well issues, they may not be thinking about in public health and individual impacts to wells. When they think about water quality, they'll be looking more regionally, not at the individual wells. So kind of a different focus there as well. Okay, working with the GSAs as you folks move forward and look at sustainability. I think it's important to understand the roles and responsibilities like we talked about before. Share information, because there is really good information that the counties have, and counties sometimes have a seat at the table in the GSA process, but sometimes it's a different department, or sometimes they're not even there. There can be things like data from well permitting programs. There can be opportunities to use maybe radio systems that can be used for telemetry for wells. There's a variety of areas, land use, where the counties can be plugged in, and where environmental health is important. Recognize and act on opportunities. Grants may be available that aren't directly related to groundwater and water supplies. They may be more recreation based, maybe more climate change based. They may be DAC based, but they may provide opportunities for water supplies. So make sure there's coordination, communication to make sure that those can come to be. And also developing sustainable water supplies requires many entities. So that's a lot of people involved, and it takes a lot of coordination to make it happen properly. It's a little bit more on engagement. How do you move forward? How do you figure out what kind of water supplies might work for your area? One is build an understanding of local water supply conditions. So this is a list of some of the documents that may be available in your area to understand a little bit more if you want to get into more details for your area. Groundwater sustainability plans are the new plans that you put together under the Sustainable Groundwater Management Act. urban water management plans are for the medium-sized and larger urban water purveyors. Been put together for a couple decades now. New ones should be coming out here pretty soon, I believe. Agricultural water management plans and integrated regional water management plans may also be available, and often other local planning documents are available. So you can read through these, get a better understanding for what conditions are like in your area, what the water supply sources are for your area, and then these plans will often also have proposed projects and actions that are already being considered by the folks that are putting these together. And don't assume that the people that are putting these plans together are talking to each other. They may not be. So if you do look through all these documents, you may find opportunities to link things together and to connect some dots that other people may have missed. Contribute towards understanding conditions. I mentioned the county well permitting databases are often the highest quality data on domestic and rural water quality. So there's a need to share information with the GSAs. There's just really very limited information out there on water quality for these rural areas. That's getting better with some of the irrigated lands programs. But to the extent that the counties, the GSAs, the irrigated land entities can work together, there's a lot of opportunities there to share data and avoid some duplication of work. The other thing that can really help a lot is maintaining and improving databases. A lot of counties have good data sets on their well permitting, but some of the older data may be on paper. And so there may be a lot of value in digitizing those and getting access to some of those older well records. A lot of times it's hard to know wells that are destroyed and link them back to the original well permit. So working on some linkages there to help people understand which wells are actually still in use. Linkage between other well identifiers, making sure we understand a well in the well permit database, how it relates to the water quality databases, how it relates to the water level databases. A lot of these databases use different identifiers, and so linking those up is a important thing that could be done. Quality control check on data. A lot of these data sources are being used for things they weren't really intended for. So there may be a need to go through there and make sure that all of the data that's in there makes sense. And then streamline sharing of information. If there are opportunities to centralize databases or provide some kind of structured sharing of information, that would be really, really valuable. Revisit well ordinances. Coordinate with the GSAs to discuss what they're seeing. There may be a desire to try to address the density of wells or the size of the wells or the total yield if they're trying to avoid additional wells going in if they're already over allocated with regards to groundwater extraction. There may be desires to look at the well seal depths, and that may be to be protective of shallow ecosystems that are using the groundwater system. Maybe they may want it to be deeper seals near sensitive surface water bodies to avoid having those wells take water from the streams, particularly in the summertime when they may be sensitive, or other local needs, and being cognizant of potential CEQA implications of going through this kind of process and moving more towards some discretionary permits here. And kind of go into that eyes wide open because it can be a real challenge there. The other thing is to track groundwater conditions. The GSAs may have tools to track groundwater levels compared to their thresholds. So you may be able to go online or get access to that from the GSAs and track the data to see to what extent you might be expecting to have issues next summer if it's dry. So you can look at the data, analyze the trends for those kind of medium-term needs for tanked water programs or things like that, and also look at long-term needs to see if you feel if the GSAs are being aggressive enough with identifying new supplies, or if they need to start looking at maybe some more demand side reductions to make sure that they don't violate some of those thresholds. And then advocate for additional supplies. There are a lot of different interests out there, not just water supply. There's flood, there's recreation, there's disadvantaged communities, there's folks that are interested in climate change, a variety of different interests out there. So anything that you see that might be a potential grant opportunity or some projects that might need a proponent to move it forward, these are all things where an advocate is needed to help get some of those things moving. The other one here I mentioned before is address demand issues if supplies are inadequate. A lot of these GSAs are really counting on floodwaters and other kind of supplies that may not be available or that may be being claimed by multiple basins for the same water, because these GSAs are really trying to avoid fouling of land and other kind of demand side reductions that can really impact communities. But it's important to be realistic about what the supplies are, and then advocate for water quality and public health in the process, and make sure that doesn't get lost. So with that, I will open up for questions. If there's questions that we don't get to today, y'all are always welcome to reach out to me.
Thank you, Jim. Great job. We have a few questions for you. The first one is from Rick Encarnacion. He says, there's a sector of the public that have concerns of desalination plants being owned and operated by private for-profit businesses, specifically with costs that are passed down to users and increasing rates. In your opinion, can this concern or issue be leveraged for local governments to gain funding for a publicly owned and operated desalination plant? Is it feasible? Also, one more question. Is it feasible for a local government or jurisdiction to venture into owning and operating a desalination plant or any major project for water supply purposes to address seawater intrusion?
Yeah, that's a good question. And you're asking a hydrogeologist and not a not a finance guy. But they are certainly very expensive water supply sources. I don't see why a public agency couldn't pursue their own desalination plant. They are expensive, but public agencies have pursued expensive projects in the past. So I think it would be feasible to do that. But I think certainly the experience of these early plants going in can be some guidance for future entities that want to go the same path or maybe a different path, depending on how those things come out. Okay.
Any thoughts about a private water company setting the rates and concerns with the desalination plant and how those? I mean, I saw the rates you showed were like $5 per month per homeowner in Carlsbad. That didn't sound that unreasonable for me from my perspective. And I don't know. Is that what are your thoughts just about the private company running the water supply?
Yeah, well, we have a lot of private water suppliers within the state. They are regulated by the CPUC. I'm not totally sure how those desal facilities are regulated. $5 per month, it's not a lot. It could always put people over the edge. Some people that are living on the edge, and it is a supply source down there that's about 9% of their total supply. So it's that incremental cost for a small portion of the supply, right? So if that grows, then that cost grows. So it's a concern. And honestly, I'm not close enough to how that's being regulated, I think, to really give a complete answer to it. But it's a good question.
Okay. Just a reminder to everyone to use the Q&A to ask any questions of Jim that you might have. I have some other thoughts. And also, I did put the link per Vicky's request in the Q&A for the drought fund grant program information related to grant loans. And so check that out in your chat. A couple other thoughts I had, Jim. Could you go into a little bit more detail about the water quality concerns for Floodmar?
Yeah, sure. So one of the issues with Floodmar is that you are recharging on active agricultural fields. And so in the unsaturated subsurface, you can have salts and nitrates primarily that are sitting in that unsaturated zone. So when you flush a lot of water through there, you're going to flush through those constituents that have accumulated over decades of time. And so at least initially, you would expect some water quality degradation. But if you can get enough water going through there over a long enough time period, you'll eventually balance out that initial kind of pulse of higher concentrations with cleaner water as it comes up behind. So it's all kind of a question of how much water is going in, what is the condition of that subsurface, and where are the receptors, and would they see that kind of first pulse of water go through.
Okay, cool. I'm wondering about the it seems like every time there's a drought, we talk about the bay and the desalination, the saltwater intrusion and environmental concerns, and about the balance between environmental water versus agricultural and residential water. How is that debate showing up right now, or is it showing up about, we shouldn't send as much water out to the bay, we should hold more back in the reservoirs and all that? Is that conversation happening at all?
Yeah, I think that conversation is always happening. I know there's just listening to the news this morning, people talking about SGMA and restrictions on groundwater, and how the federal government should provide more water to farmers, more surface water, imported water to farmers to replace that. There's always a very challenging balance between the needs of the ecosystem and the needs of urban and agricultural users. I think we'll probably always have. Okay.
I think Dave had a comment or a question. Dave, did you want to pop back on?
Yeah, so I don't know, I've disappeared.
Okay, well, I'll find you.
Anyway, my question, Jim, is actually I have a couple of questions. One is in your land repurposing part of your presentation, you talked about fallow fields and stuff, and I'm wondering if what's been happening in the Central Valley is a lot of crop conversions from crops that are seasonal to nut crops and orchard crops. And how is that affecting the ground?
Yeah, that's a good question, right? So if you have a field of sweet potatoes and it's going to be dry, you can just not plant your sweet potatoes that year, right? But if you have a field full of almonds, you have to water those almonds, or you're going to have a substantial financial loss there. So it certainly makes it harder to fallow land as that demand gets harder and harder by more and more permanent crops, as the growers try to find the best return for their ground there. It also drives a lot of the GSAs to look towards a lot of water trading opportunities within the basin. So trying to figure out ways, if everybody has to cut back groundwater use by a certain amount, can that person that has crops that they can't fallow kind of buy somebody else's share and then use that water on their property there? So I think that's something that those kinds of water markets are water trading or water allocations are things that are a lot of GSAs are trying to struggle their way through how to do that in a fair and equitable way.
I'm wondering, Jim, have you looked into your crystal ball, and if we go down this drought world, for another 5-10 years, and we start kind of running out of water, what's the future going to be like?
Yeah, that's a good question. So when water supplies get tight, it's typically the agricultural users and the ecosystems that kind of take the first hit. And a lot of what is built on SGMA is a pretty delicate balance between what's required of the GSAs under SGMA and then the existing water rights structure. I think water rights, in particular groundwater rights, would probably have to be another couple of training sessions. But the SGMA doesn't authorize water rights to be changed. So water rights aren't being changed, even though these entities are telling people they have to cut back on water. And it gets really challenging for a lot of these entities to figure out how to do that. And you can think about a lot of these basins that may have a lot of open range land that's not being irrigated, things like that. And those folks have access to groundwater. They maybe could be growing something else and they may want to in the future. And when the drought comes and people have to start making these kinds of reductions, and the GSAs have to start telling people, you have to cut back or we're going to hit these thresholds and the state's going to come in. I think that's honestly where we start getting a lot of the lawyers involved. And I think you'll start seeing a lot of lawsuits, and you might unfortunately see some basins start going down an adjudication process, which is a process where the court comes in and tells people how much water they should be able to use. And it's a process that takes decades and millions of dollars, and a lot of what Sigma was trying to avoid, but we'll see if we can avoid it or not.
All right. So pray for rain. Got it.
Yes.
Yeah. And then I have another question, Jim, when you talked about groundwater desalination being less energy intensive, is there a trade-off with, if you start pumping more water that's like seawater intrusion areas, do you get a heavier seawater intrusion, and is the problem going to get worse?
Yeah, so that's a good question. So where the example that I gave with Eastern Municipal Water District, they're actually well inland. They're, I don't know, 100 miles from the coast or something like that. So they don't have seawater intrusion problems. The salt that they have in their subbasin, a lot of it is naturally occurring. Some of it is from kind of the cycling that occurs as water gets reused and salts accumulate over time. So they don't have that issue. If you are near the coast, then yeah, you'd have to be careful not to do that. And entities that look at desalination, like the one in the Monterey Marina area with wells, they try to place those close enough to the ocean so that they're taking pretty salty water there, and it's not quite the same as what Eastern is doing.
Thanks.
All right, we'll give a final check here. Any Q&A? Anybody want to ask one final question before we wrap up? I don't see any more questions coming in, so I think at that point we'll thank Jim. I'll turn it back to you, Vicki, to wrap us up.
Thank you. I just had one brief comment to kind of follow along with the groundwater recharge piece that Jim had spoken about. Sometimes the soils in the area may not be conducive to, seeping or percolation, depending on the soil types in an area that may need to have groundwater recharge considered. And so sometimes you do see proposals for dry wells, not injection wells. That's different and require a different set of permitting from the state. But dry wells are, able to be constructed, installed as long as ordinances allow, with approval from the California Regional Water Quality Control Board under a monitoring and reporting program. And so we do have a small pilot program of that, of a few dry wells to help with recharge in our northeastern part of our county in Merced County. But I just wanted to bring that up as well, that if you do have proposals of dry wells to be installed for that purpose for groundwater recharge, you definitely want to make sure that they have been in touch with the Regional Water Quality Control Board and are under a monitoring and reporting program. And I just wanted to thank everybody very much for your time today and joining us. And Jim, thank you so much. That was an excellent presentation. I really appreciate your time.
No, thank you.
All right. Back to you, Dave, to wrap us up.
And I echo that. Thank you, Vicki, for bringing this this training to us, and Jim, thank you for your taking the time to put together an excellent presentation. I realize that just about every subject that you covered could have spent the entire time.
Yeah.
So, great job. I'd like to remind everyone to go to ccdeh.org and do your evaluation so you can get your continuing education points. Letters just recently are getting ready to go out for the 2021 folks that are due for registration. And with that, I'll say goodbye.